Alright, so now we're going to go over the Lorentz Transformation. Now, we're going to base a little bit off of this on the invariance of the interval from before, but we're still using the same inertial reference frames, the laboratory frame and the rocket frame. Now, to start us off, we're going to put those frames right on top of each other and start a point right in the middle of them. Now, that point is going to be moving with the rocket frame, so at the same rate. This is to the effect of making x prime equal to 0. So, with x prime equal to 0, we can essentially take our equation for the invariance of the interval, t squared minus x squared equals t prime squared minus x prime squared, and take x prime squared out. Equation's still too complicated. We need x squared to go away. So, what's a really simple thing to deal with x and t? Position and time, velocity. So, x divided by t equals beta is what we're going to call velocity for in terms of purposes of this proof here. So now we're going to rearrange that until we get x squared equals beta squared t squared. Clearly, just the movement of the t in a square. So now that we have this equation, we don't need this one. Also, what's useful to know is x equals beta t. That'll be useful later. Anyway, so now starting from this equation for the invariance of the interval with x prime equal to 0, we get t squared minus beta squared t squared equals t prime squared. So now with a bit of factoring, this is going to become t squared times 1 minus beta squared equals t prime squared, and t squared equals t prime squared over 1 minus beta squared. Now take square root of that, we get t equals t prime divided by the square root of 1 minus beta squared. And now, the reason that we have x equals beta t is that we know what x is relative to t. So that means that if we just multiply t by the value of beta, then we get, well, x equals beta t prime divided by the square root of 1 minus beta squared. So, that's our value for x. But now the issue was that we had x prime equal to 0. That's not useful, because the issue is that now there's a hidden term that was knocked away because x prime is equal to 0. Who cares if they were? Because, these terms were being hidden. A x prime and b x prime. We need to figure those out. But now we get to go back to one of our more original equations, the invariance of the interval. Adding this back on, minus x prime squared. So we can use these equations and input our values for t and x into t squared minus x squared, and essentially get, in parentheses, t prime squared, or rather, the whole thing is going to be squared, so we don't need to do that right now, divided by the square root of 1 minus beta squared, minus ax prime squared. That is the value of t squared. Then, we are going to take the x equation and square it as well. Beta t prime divided by the square root of 1 minus beta squared minus bx. Don't confuse b with beta. Two different letters. Bx prime squared. And that's all equal to t prime squared minus x prime squared. So now, when we factor these out, it's going to be a massive mess, but what we're eventually going to end up with is t prime squared plus 2 times a minus beta b and times x prime t prime, and that whole equation is over the square root of 1 minus beta squared. And then onto the end of this equation, we're going to slap on plus a minus a squared minus b squared times x prime. And so now, there are a few crucial things in this equation that we have to do to make it equal to this equation up here. So if we're going to make these two things the same, there are a couple things that really need to happen. First of all, as you can see, there is an x prime t prime. Nowhere in this equation is x prime multiplied by t prime. So something in this term needs to happen to make it go to 0. Secondly, we have a positive x prime over here. So we need to take this x prime and make it more like this x prime to make it happen. T prime is already as t prime would be, so as you can see, t prime is up there. So that means to make this x prime squared more like this x prime squared, this term has to go to -1. So we can just kind of flip that, and then we also have to take this a minus beta b and make that equal to 0. So let's put that into action here, shall we? First of all, a equals beta b. It must, or else nothing of use will happen here. And then b squared minus a squared has to equal 1. But then again, if b squared minus a squared equals 1, then, well, you know, in theory, we should still have a, well, you know, b minus a, well, yeah, b squared minus a squared must equal 1. So, now we get to do some substitution. We have a useful equation up here. A equals beta b. We have an a value here. So that means that to make this into one variable for us to use, we're going to make it b squared minus beta squared b squared equals 1. And now we get to do some factoring. B squared times 1 minus beta squared equals 1. And then we get to take that and essentially just, divide, which will give us, divide and square root, so I'm going to do those both at the same time. B equals 1 divided by the square root of 1 minus beta squared. And that's our value for b. But now we need a value for a, but once again, this equation comes in use. This is really convenient, because we can just take our value for this equation and multiply it by beta, which means that a equals beta divided by the square root of 1 minus beta squared. And so now we take these values and input it to the earlier equation we received, and we will receive the Lorentz Transformation equation, which is t equals t prime divided by the square root of 1 minus beta squared. And then we take our value for a and multiply it by x prime. So minus value for a, beta x prime, because it's been multiplied in, divided by the square root of 1 minus beta squared. Then we also have to get our x value out, which is x equals beta t prime divided by the square root of 1 minus beta squared from before. And then we subtract x prime divided by 1 minus beta squared. And that equation there is using the b from before. So this whole thing is the Lorentz transformation. That's going to be useful for when we need to take coordinates from one frame and switch them into the other one. Thank you very much. I'm Miguel.